Hello, everybody. Sorry, that may have been loud. Is everybody having a good conference? I've really enjoyed this conference. It's really awesome to be back in Israel. I want to thank Adi and Michael and all the organizers for putting this together. It's been really great. So the opening keynote, Jason told you about 25 of the 25 best parts of C++. It's sort of fitting that I'm just going to talk about one then. I don't know if I think it's the best, but I think it will be the most impactful. I think long term it might be the best thing that will happen to C++ since the first C++ standard has been put out. And that is modules, which is all that we're going to talk about today. So first, a little bit about me. So this is a diagram of the C++ Standards Committee that somehow works its way into all of my talks. So I work at NVIDIA. I'm the head of the CUDA C++ core libraries team there, but my real job is doing C++ committee stuff. So I am the chair of two subgroups on the committee, the Library Evolution Incubator Group, which is the SG18, the box at the bottom there, and I'm also the chair of the Tooling Study Group, which interestingly spends most of its time these days talking about modules. And that is sort of the basis for this talk. We realized that modules was going to have a huge impact on the C++ ecosystem. So I wanted to get out there and socialize this feature and make sure that everybody knows what is coming so that you can prepare for it. All right, so as I think I may have mentioned earlier, I think C++ 20 is going to have a huge impact on the language. It's going to be as big of an impact as C++ 11, maybe even larger. There's a number of large language features that are going in, concepts, coroutines, improved context for support. There's also sort of a redesign of the standard library with ranges. And there's also modules, which I'm going to argue is the most impactful feature in C++ 20. So what are modules? Modules is a new compilation model for C++. And it's a new way to organize C++ projects. So let's look at one example that we're not going to dive too deep into, but I didn't want to have too many slides without showing you some code. So here's a very simple project. I've got some header math.hpp that declares a function square. Then I've got a source file, math.cpp. It includes that header file, and it defines the square function. Finally, I have a function main.cpp, which includes math.hpp and uses this square function. It's pretty straightforward. All right, so this is what that looks like in the modules world. So instead of a header file, I have this math.ixx. This is what we call a module interface unit. The first thing in this math.ixx is this export module math. So I say, hey, I am a module interface unit. The type of, the name of the module that I am an interface unit for is math. And then I have my square function again, but this time I say export square function. Then I have this math.mxx file instead of a source file. And in this file, I have a similar declaration at the top saying I am the file that defines the math module. And then I have the definition of the square function. And finally, in main.cpp, I use this module by importing it. All right. So, as I said, I think modules will have a greater impact than any other C++ feature since standardization. Let me walk you through some examples to explain why. So, C++ 11 introduced a threading library, the thread header. So this changes how C++ code is written, right? Previously, you would use pthreads, or you would use your the Windows Windows OS threads, or you do something like boost threads. And now you use the standard libraries threads instead. So it changes how you write your code. That's an impact. It's not a huge impact, though. Well, how about lambdas? So lambdas, they change how your C++ code is written, but they have a larger impact too because they change the very syntax of the language. So they also change how C++ code is parsed, which you might think would just affect compilers, but it actually affects a lot of things. It affects your IDEs, things like syntax highlighting, static analysis, documentation parsing, etc. If anybody uses Doxygen in their project, they're probably familiar with how poor Doxygen can be at parsing C++11 code until very recently. So what about modules? So modules, as we've seen, they change how C++ code is written. They change how C++ code is parsed, which, as I said, affects a bunch of tools. They change how C++ projects are compiled. This means they affect your build systems, your distributed build systems, your continuous integration systems. They affect how C++ projects are organized, like the very structure of your project, the types of files that you put C++ source into. That affects your packaging and distribution of your projects. And they change how C++ projects are consumed. This affects things like dependencies, both your downstream dependencies and your upstream dependencies, those things that you use and people who use you. They affect other languages that use C++. It's going to affect, obviously, tooling, any sort of tooling that needs to know how to consume a particular file in your project will be affected by modules. So again, I'll say I think modules will have a greater impact than any other feature added since C++ 98. Nothing else has affected the very compilation model and the way that we organize source code. All right, let's talk about today's compilation model. So what is the compilation model today? Like, how do we organize our C++ projects today? This might not be something that you've thought about a lot because it's very innate in what we're doing, and it hasn't changed in 40 years. In fact, C++'s compilation model is C's compilation model. It's really, really, really old. So, as I tend to do in all my talks now, I will now read to you from parts of the standard. So the text of the program is kept in units called source files in this international standard. This sentence is actually very, very critical because it tells you what the international standard specifies, which is the text of a program. So a source file, together with all of its includes expanded, is called a translation unit. Most of you are probably familiar with this term. I will refer to it in some of these slides by the abbreviation TU. So pre-C++ 20, we had one type of translation unit, what I will call non-modular units. So these were just like .cpp files. That's it. Now you might notice there's a lot of blank space on this slide. We're going to fill it in throughout this talk. So a program consists of one or more translation units that are linked together. And previously translated translation units can be preserved individually in object files or in libraries. So this model of compilation, we're going to call it textual inclusion. And let's go through a little example of how this works. So I've got some simple project where I have two source files, a.cpp and b.cpp, and I've got 4 headers. One header for each one of the source files. Then I have c.hpp, which is some header-only utilities. And then I have a header lib.hpp for some library that I'm using. That library is some translation unit that's been preserved in the library. So a.cpp includes a, b, and c.hpp. And b.cpp includes c.hpp, and b.hpp, and lib.hpp. Note that the order of includes in b.cpp is slightly different than the order in a.cpp. All right, so the first step in compilation is to pre-process the source files along with their headers into translation units. So let's do that. So then we end up with this. We have textually included each one of the headers into these translation units. Next step we will compile the translation units into object files. Okay? Now, we link together the object files that hold the translation units. And now we have some executable that's linked against this shared library. So there were 3 steps here. We pre-processed the source files into translation units. We compiled those translation units, and then we linked them. It's all very simple, easy to understand. Here is a little makefile for this project. It has 3 rules. 2 of these rules describe how to build the object files. So how do we build the object file for a.cpp? It just has 1 dependency. Very straightforward. Same for b.o. And then finally, we link together those 2 object files into the executable. All right. So this is a very simple model. That is one of its benefits. But there are some problems with it. Mainly, headers are kind of terrible for a variety of reasons. So first of all, headers are slow to compile. Who here thinks that their C++ code does not compile fast enough? Yeah. So my projects can, like, if I build the work code base on my laptop, it takes like 40 minutes, which is way too long for me. All right, so why is textual inclusion slow to compile? It's because of this. It's actually right in the name, textual inclusion. In that first step, that pre-processing step, you include the text of those headers into each one of your translation units. So each translation unit, each source file that uses a header has to parse and build the AST for that entire header unit. So this has some pros in that it's embarrassingly parallel. Like if I have 7 source files that are using like 3 headers, I can compile each one of these source files independently. But the downside is those 3 header files are going to be compiled 7 times. And when you get up to scale, that is very expensive. All right, second problem with headers, ODR violations. So what is the ODR? The ODR is one of the fundamental rules of C++. It's defined here, basic.def.odr. It says basically an entity in C++ should not be defined more than once. But no diagnostic is required if it's been defined in multiple translation units. This is called ill-formed, no diagnostic required. This is like compiler undefined behavior. Basically, it's saying your program's invalid, but we don't know how to diagnose it. So if you do this, bad stuff happens. So let's look at an example of that bad stuff. So let's say that I've got some tree node class that usually just has 2 members, but if the macro debug is defined, I add some other members that give me some debug information. So if I include this header in one translation unit where I define this macro, I will get one definition of this type. And then if I include it in another translation unit that does not define this macro, I'll get a different definition. And then what happens if I try to pass an object of this type from that was created in a.cpp to b.cpp? Then my program's going to blow up because these 2 translation units disagree about like the size and layout of this type. That's bad. And your compiler doesn't really know how to diagnose this. All right. So headers are not encapsulated. So when you put something into a header, unless it is a private member of a class, typically there's very little you can do to prevent it from being used if you don't want it to be used. So for example, like if you have some function that's just like an implementation detail, or some type that's just an implementation detail, if you need to expose it in your header, you are making it part of your interface. Now, you've probably seen or used in your code base something like a detail namespace or an implementation namespace or something horrific like this, or ugly identifiers to try to keep people from using stuff that you're shipping in your headers. I've done this too. It doesn't stop my users from using these things. It's really quite awful. What we really need is a facility similar to access control for classes, but on the granularity of our units of code. All right, so cyclic dependencies. Headers let you write cyclic dependencies. typically this comes up when you have like forward declarations. So like here I've got a.hpp, which includes b.hpp, has a forward declaration of y, and then has some struct x that has a pointer to y in it. And then in b.hpp, I include a, and I've got a forward declaration of struct x, and then I've got a struct y that has a pointer to x. So this code works with headers. Like you can include either one of these headers, you'll get the definition of both of these things. But there is a cycle here. These two headers depend upon each other. Headers are also order dependent by nature of them being textually included into your program. So here I've got two headers and one source file. The first header, a.hpp, I declare some struct. And in the second header, b.hpp, I have a function that takes that struct but doesn't forward declare it. And in c.cpp, I just happen to include a before b. So I don't run into any problems yet because I just happen to have included the thing that b needed before I used it. And if everywhere that I include a and b, I always include them in this order, everything's fine. But if I include them in a different order, then I'm going to get an error. And I'm sure most of us have run into issues with this in our code bases at some point, where you were missing an include in some particular header. All right, so headers are terrible. I think we can all agree to that. Yes? Yeah? All right, good. Okay, so now let's talk about using modules. So this talk basically breaks down into two parts. The import part of the talk, where we talk about how we use and consume modules, and the export part of the talk, where we talk about how we write modules. So we will start with import. So import is a new keyword in C++20, and it is, you can think of it as like a replacement for include. So instead of including some header file, you import a module by name. So now let's take a look at the compilation model for modules. I think that's the easiest way to sort of give you an overview to how it works, because it's not as straightforward as the textual inclusion model. So when importing, the compiler finds the relevant module interface unit, which we're going to call .ixx in this presentation. And that .ixx, as we saw with a few examples earlier, describes which entities are exported from the module. So the module interface unit is sort of similar to a C++ header, the sort of the replacement for headers. But unlike a header, a module interface unit is a separate translation unit, not text that is included into each TU. So when you import a module, you are not textually including something. You have another translation unit that's going to be compiled, and you are using entities from that other translation unit. Module interface units need to be pre-compiled into a non-textual representation that is fast for compilers to look up in and use. We call these compiled module interfaces, or CMIs. So this is a new step of compilation. You need to pre-compile your .ixx's into CMIs. So let's do that now. All right, so now we have CMIs for each one of our module interface units. So now we do pre-processing as usual, but we're not actually including anything into these files, so we don't dump up, the text of a bunch of headers in here. All right, so next, after we've pre-processed, now we don't need the actual module interface unit source files. We can get rid of those. We can just work with the CMIs. And now we need to compile our two translation units, and we also might need to compile our CMIs. This will depend on your compiler. Some compilers, you may need to compile your CMIs to object files because there may be metadata, such as debug information, that you want to have preserved through to the link. On other compilers, you might not need to compile your CMIs to object files. For right now, let's just assume that we're going to be compiling our CMIs to object files. This is the thing that you should do with Clang today, and that's the implementation that I've mostly been working with. All right, so we had CMIs, and we had .mxx's, module implementation units. We'll explain more about what those are later. And these are all, those are just source files. and we're going to compile all of these to object files. So now we have .i.os for the object files for the interface units, and we have .m.os for the object files for the implementation units. All right, and finally, now we just link all these things together, and we get our executable, just as before. A few more steps, but we get the same product in the end. So the key difference here is that we have a new step. Okay, cool. We have a new step in the compilation process, which is this pre-compilation of module interface units to compiled module interfaces. All right, now we're going to look at an example of what a makefile would look like for this. Unfortunately, it doesn't fit on one screen. Okay, so first, this is what it would look like to compile the CMIs from the module interface units. So if like Clang has a flag pre-compile, it's similar to the -C flag that you would use for taking source units to object files. But here, we're outputting CMIs, which is it's not a binary representation necessarily, but it's some efficient, non-textual representation of your module interface unit. So once we have these .cmis, we need to compile them to .os. So here are the rules for that. And then we need to compile our module implementation units, the A.mxx and the B.mxx. And these depend on the CMIs because those implementation units imported some of those modules. So they need the CMIs to figure out what stuff was in those modules. And then finally, we have the link here, which has a whole bunch of things. It has the object files from the implementation units, and it has the object files from the interface units. All right, yes, I know, this is not as straightforward as you might like. Yeah, question? I'm sorry, can you repeat the question? The question is, are the dependencies are duplicated in the text file and the make file? Yes, I have chosen to do it this way. This is what you would call it the explicit model of how to deal with modules, where you explicitly encode your modular dependencies into your makefile system. So the makefile we saw earlier for the textual inclusion did not encode any dependency information for the header files into the makefile, because typically you don't do that explicitly today. You might use like a compiler's -mmd mode to do that, but you normally don't like explicitly encode that. That might not be a world that we live in any longer. We may now live in a world where you want to explicitly encode your dependencies like this. All of your dependencies like this. All right. So, yeah, another question? Yes, we will talk about that later. There are pros and cons to that, but we're going to talk about that later. The question was, will compilers add some sort of dependency scanning mode for modules? And yes, they will. That's been something that's already been done for GCC, I believe. I don't know about Clang. And some build systems like CMake are already working on integrating in those dependency scanners into their build system. But we will talk about that later. Maybe. Okay, so let's compare the algorithmic build performance of textual inclusion to modular inclusion. So as we said earlier, with textual inclusion, the pro is that it's embarrassingly parallel. We can compile all of these source files independently of each other, but we are compiling the headers multiple times. With modular inclusion, we pre-compile each one of the interface units just once. However, things are no longer embarrassingly parallel because like we need to do this explicit pre-compilation step, and we have multiple consumers of each one of these headers. We only want to do that pre-compilation once, which now means that these source files depend on something happening. And so you can no longer just do these all independently, or you lose the build performance benefits of modules. All right, so let's go back to this table. of the types of translation units. So we have added 2 new types, module interface units, which are units that start with this export module name. And I'm calling them in this talk .ixx's. And their build artifact are CMIs and potentially .os. There's going to be exact